Tom. Welcome everyone. I love this idea, learning in the laneway. Isn't it fantastic? The Epicurean heart of our city, Melbourne, a tourist attraction in itself, is the laneways of Melbourne. And what better place tonight to get away from all that online stuff, get out of the computer and away from the cloud, actually meet some real people. It's fantastic. So I'm very excited to be here tonight. So tonight we're going to be talking about citizen science, or astronomy for all. Astronomy is a fascinating thing. Like for eons and eons, people have been looking to the skies and connecting with the universe around them, pondering what's out there, wondering how it all came to be there. It creates in us an incredible sense of emotions and passions. So astronomy is something I connected with as a teenager. And as you do, you go through life, you go to university, and look at all the things you're going to do, and you come around to later in life and there's a lot of things you haven't done, and you think, well, it's about time. Maybe I reconnected with some of those dreams I had when I was a kid. So tonight, the agenda, if I can throw out the boring agenda slide, we're going to go through a bit about my telescope, and we're going to talk about some of the forces that are happening in the world today, the new normal. Right? So you've seen Facebook and Twitter and all these kind of things. What does that mean? Astronomy today, so we're going to go through Astronomy 1.0, 2.0, 3.0 and talk a little bit about that. And that'll probably take about 20 minutes just to run through that. And then we're going to talk about, then we're going to participate in a real NASA science mission tonight. Now, I just have to interrupt here for a minute because it's a very, very sad story is that it's actually been raining for the last couple of hours in New Mexico where my telescope is, and that's what the all-sky camera looks like at the moment. But fortunately, 3 nights ago, I took a whole heap of photos that we can actually use a little bit of play around with, and you can see what an asteroid looks like as it goes across the night sky. So, so that's what we're going to cover tonight, and try and keep it upbeat. I'm happy to take questions at any time, but let's get back to the presentation. I'll just give you a bit of an overview of where we're going tonight. So what's going on in the world today? So it's no surprise that you're an intelligent-looking bunch. So there's no surprise that universities have graduate courses, they have postgraduate courses, they have facilities and equipment that they use. So there's facilities and equipment that universities have to supervise. There's research that they do, and a lot of their kudos and their reputation in research and science is due to the research that they do. And also they have outreach programs to create a pipeline of students to bring people into the university program and stimulate. One of the incredible things this nation is facing is a shortage of skills, and we've all heard it, in maths, science and technology. And every nation is faced with this in the competitive environment we live in today. How do we reach out and capture the young hearts and minds for the next generation of science research to make us a more productive nation? You've heard of Australia referred to as the quarry of Asia. Well, how do we change that? How do we capture the young hearts and minds for another generation of science? So it's quite key to what universities do. So in astronomy, we're seeing mega science projects. We've got space telescopes up there now that are torrents of data coming down, like the Kepler Space Telescope is photographing 160,000 stars continuously to look for little blips in their light curves, so that as exoplanets go in front of the star. So that's creating torrents of data. Now, how many scientists can look at it at any one time? There's lots of leftover data, so we're going to talk about that. Social media has really changed, and astronomy is the one science where social media is really strong and engaging people. We've got a lot of communities. I'll talk about those in a minute. And collaboration has been something that's come out of the IT industry and created this whole new ability to put a scientist in a classroom via a video conference or via Skype or WebEx, all those technologies, Google Hangouts. In the external environment, we've got a sovereign debt crisis, the governments are running budget deficits, we've got research funding under pressure, we've got literacy and numeracy under pressure, and really maths and science skills are what's going to drive our innovation growth. So, I was a 1.0 astronomer. At the age of 15, in 1975, I lay in my backyard at 1 o'clock in the morning in a sleeping bag, counting meteors going across the sky. I had a book, dusty old book from Patrick Moore called Southern Astronomy. I was fascinated by this. But there was no internet. I couldn't tell anyone. I couldn't tweet it. I couldn't say I saw 15 meteors in 1 hour. Who wanted to know that there was a 15-year-old kid in his backyard that's sleeping back counting meteors? You know? As a 1.0 astronomer, a 1.0 astronomer, if you like, we play with some pictures here, but the lonely person on a cold mountain at the eyepiece of a telescope. But that's what it was like, you know. You often hear stories from the astronomers about bumbling around in the dark, looking, almost falling out of the cage and crashing to the floor of the observatory. It was at the eyepiece, and they used to have glass plates that they'd take photos. And you might have heard of some of the stories around the discovery of Neptune and Pluto, where they're flicking these glass plates from night to night, just watching for something. We're going to do something similar to that tonight. It's all going to be done on a computer. So, if you think of these as 3 different paradigms, so Astronomy 1.0, the lonely person on the mountain. Each paradigm, as it's shifted, there's been a changeover point or a threshold. It's been a trigger event that started the next paradigm, if you like, that's come in. Now, John OSullivan from the CSIRO was a radio astronomer who worked at Parkes. You know Parkes, the dish, you've seen the movie. And amazing, clever guy. In doing radio astronomy, in wanting to separate out separate channels from different antennas and look at how they were performing and separate out the noise from each channel, he invented the codec that brought us the wireless internet. Now, he recently, CSIRO, recently won a patent battle with all the big players who use that codec in their mobile devices. So CSIRO picked up $200 million in patent revenues from that one discovery. But if you like, it was kind of here. This was the first trigger event, the start of the internet. So as I said before, I couldn't tell anyone about what I was doing in astronomy because there was no one out there. The internet wasn't invented. So as computers came along, the next little milestone here was the SETI at Home. Does anyone remember the SETI at Home project? You download a little piece of software and put it on your computer and you'd get information about the signals they're looking for search for extraterrestrial intelligence. And you could process that on your computer and send the information back. And if they'd found ET on your computer, you would have been celebrated as the Jodie Foster of Melbourne, the first contact. Sorry, moving into the movies there for a while. I don't know how much good the science is in movies these days, but that was the second milestone. And as we moved into Astronomy 2.0, we got to a point where the internet was there and people were starting to connect. People were starting to set up blogs and talk to each other about astronomy, and astronomy leads the way in social media today. So about this time, also the Hubble telescope was up there. It had a little problem when they launched it. A couple of the engineers said this mirror's not right, and one said it was right, the other two said it wasn't. They put it up there and found out the one they overruled was correct, and they had to send the space shuttle up to put a correction plate in it and focus the image train because it was out of alignment. It cost a fortune, but the images that came back, the pillars of creation, all those stunning Hubble images you've seen, created a whole new interest in astronomy, the beautiful, stunning photos, and it started to gather people around it. So the emergence of the astronomy blogs, the Phil Platts, the Fraser Kane in Universe Today, Dr. Pamela Gay from Southern Illinois University, the Star Strider at Twitter. Those three people, Chris Lintott, there were a couple of others who really captured this space and started to create blogs and interests around astronomy. On top of that, all these space telescopes are starting to bring incredible amounts of data down. And the internet, from that period, the internet became really pervasive. Nothing surprising there. So as we move from Astronomy 2.0 to 3.0 here, the first little hint was the arrival of Facebook, where all of a sudden everyone's got the internet, but now we can connect and we can do social media and we can do all sorts of stuff. And as we moved out of that into the full 3.0 astronomy, now we have virtual star parties in Google Plus that are happening around the world. People can collaborate. I have put a university professor in a classroom with Jarrigan College in North Queensland, the Aboriginal school up there. It's an amazing story behind that school. But all of a sudden, this collaboration piece is part of this now as well. So we've got leftover data that we can mine for extra discoveries from all these space telescopes. We've got data that's too much for one scientist to handle. So what do? Right? You organise it all, you create a little pool, you'll see later. We'll actually have a go at one. You can actually farm that out to a whole heap of people who have an interest in astronomy, and all of a sudden this SETI at Home project we had back here in Astronomy 2.0 has become a whole heap of citizen science projects. This has now moved out of astronomy into earth sciences as well. There's one that you can go in and try and sequence some DNA for a cancer discovery, and you can run the same type of SETI program on your laptop for sequencing DNA, sequencing proteins for cancer research. So there's a whole heap of things. The people who have busy corporate lives, but you go home and watch TV, or you can sit up later tonight and watch Cadell Evans chase Bradley Wiggins up a hill. Oh, sorry, it's not tonight's a rest day, tomorrow. And you can do some of this while you're on your laptop in front of the TV. And also what it's brought us is telescopes in the cloud. So the ability to remotely control infrastructure and to do what I'm doing tonight, which is to use the telescope remotely from my beautiful little MacBook Air. So, as I said, back in 2004, I was involved in a citizen science project which took about 600 photos of the sky in one night, but there was only 3 scientists. So how were they going to get through 600 photos a night? So what they did is they took 3 little mosaics, sent them out to volunteers. There's about 200 volunteers, they're all logged in, and we'd just blink the mosaic photos and see what moved. If anything moved, we'd just tag it and report it. Citizen Science Project. And this is how I got excited about citizen science, because one night in, I think it was the 1st of March 2004, I discovered this moving in an image, and that was the asteroid 2000 EV70, which is now known as 162422. So they have these funny numbers that they apply. When they discover an asteroid, they give it the year and some numbers to categorise it, when it was found, what month of the year. After it's done about 2 orbits around the Sun, and they feel they know the orbit well enough, they make it a numbered object. And then later, once it's done about 4 orbits, they can actually name it according to some protocols that they have as well. So this got me flat out excited. This is where I reconnected with my passion as a teenager of astronomy. So
how do you prove that was that comet?
Yeah, we'll have a look at that. So, what happens is that this is a process called astrometry, which is plotting the orbit. So there's a lot of math in it. There's about 8 or 9 different variables, because they're elliptical orbits, and you've got the center of the elliptic, and the period, and all that sort of stuff. What happens is a process of creating an ephemeris, which is the orbit. So if you can imagine, an orange, for example. This is a cup, but imagine an orange with all the segments of the orange. Right, so the Earth sits on a 23 degree angle. The segments of the orange, if you're talking 360 degrees here, so what they do is they divide up the 360 degrees into 24 hours, and then that's what they call right ascension, and then from the equator to the pole is what they call declination. So the background stars typically don't move that much, they just catalogues every now and then, but the background stars don't move, so they know as the Earth turns what the background stars are telling them, and then they can get a right ascension declination position for that asteroid, and then work out what direction it's heading in, and then they can plot that over a period of time and reduce the amount of errors, and then when they'll be looking for it at a spot 3 years later when it comes back around, and I happen to be looking at that spot that night, and they picked it up and they go, yeah, well, this is okay, the uncertainty here, this is the zone, this is most likely that object, and then mathematically they prove. Is that a reasonable explanation? Not too complex? Not scaring you in science here? So, this is the world we live in today. Simplicity is the key. Your iPhone, it's easy. If it's not easy, we don't do it today. Video is the king. A lot of collaboration today. Video interaction, collaboration around video is really key. Crowdsourcing is a channel. So, in the world we live in today, if you don't know something, you've just got a tweet. Can you help me with this? And someone will come and tell you. Crowdsourcing itself is, there's a website called Kickstarter, I'm not sure if you know that, Kaggle. There's a whole heap of different websites now that are in this crowdsourcing. So, if you don't know how to build a bike, well then you say, I want a bike, 2 wheels, racing handlebars, blah blah blah, and guess what? Laneway Cafe, actually I've got one of those, and sign here. So crowdsourcing is about going out to the crowd and putting it out there, leveraging the power that's out there in the crowd. And this is partly what we do in citizen science. We leverage the power of people that are interested in science. And collaboration is how we get things done. So, any questions on that? Does that kind of, you understand that experience of where we are today? And this is impacting astronomy, it's impacting science everywhere. It's not only astronomy, but astronomy, as I said, has been one of the leaders. So, tonight, you're going to be a 3.0 astronomer. Alright, so, firstly, I need to tell you a little bit about asteroids. So, we're going good for time here. So, asteroids, what are they? Anyone know? Anyone know what an asteroid is?
Smaller than a planet.
Smaller than a planet, yeah?
Like a moving object made of iron.
Yeah, iron, yeah. So it can be iron, there are other types of ones. There's 3 different types there, you can see. So it's often described as the leftover debris of the solar system between Mars and Jupiter, or a planet that was there and got whacked and broke up into little bits. So, the jury's still out on exactly what the asteroid belt is, but it's full of a lot of different things. So Jupiter has a strong influence on the whole of the solar system, and it kind of vacuums up and ejects things, because it's so big and its gravity is so strong. So there are a number of different types of asteroids. So Apollos, Amors and Atens, they're just 3. There's more than that, but they're the main ones. And they're what they call main belt kind of asteroids out there. Trojans are asteroids that are near big planets. So if you imagine Jupiter's here, and the sun's over there, and there's a thing here where the gravity from Jupiter and the gravity of the sun is the same. And that's called the Lagrange point. There's one of those ahead and behind the planet as it goes around the sun. And anything that's just wandering around can get stuck in there. Let's call it Trojan asteroid because it follows around in the Lagrange point. So that's a different type of asteroid. They're quite interesting. And then there's near-Earth asteroids and PHAs. So the near-Earth asteroids are ones that come near the Earth. There's some specific criteria for that. But potentially hazardous ones are ones that are greater than 100 metres in diameter and come within 0.05 of the distance between the Earth and the Sun. So because Jupiter and Mars kind of influence their orbits sometimes, that's considered a fairly interesting distance where we need to keep an eye on them. Right, so how many are there, you might like to know? So there's about 1,300 in that category. So the Minor Planet Centre tracks the asteroids and comets, and they publish it on their website. All this stuff about NASA's keeping stuff secret from us. Every one of the 500,000 asteroids are in there, and you can look them up anytime you like. So there's no conspiracy theories here. You often hear bloggers talking about it. So the Minor Planet Centre does a great job of doing that. There's lots of surveys that scan the night sky, and amateur astronomers like myself still play a significant role in that. So, in 1989, asteroid, as I said, they give it a year number and a couple of letters depending on which month it was founded. This asteroid, now known as Asclepius, occupied the same spot in space and time that the Earth occupied 6 hours later. So it missed us by 6 hours, and it was 300 metres wide. So it was sort of about 4 MCGs in diameter, if you like. It was a big one, and it missed us by 6 hours. And at that point in time, the powers that be, NASA and a lot of people in the US government said, that's kind of a bit scary, we probably should do something about this. And NASA set a goal by the end of that decade to find 90% of the asteroids that were greater than 1 kilometre. Well, it's, yeah.
Sorry, was it found before it got there?
After it went past,
okay.
Yes, unfortunately. Yes, that was even scarier. So, yeah, I think it was the day after they picked it up in a survey. Now, bearing in mind the first asteroid was discovered back in 1850, right? So, I think there's Eros from memory. And, so the really big ones were quite obvious because they were moving in the heavens and the astronomers could see them. It's interesting today because as the technology gets better and better, we find smaller and smaller ones. Therefore, the likelihood of the smaller ones hitting us is actually higher because the old bell curve kind of thing. In fact, in 2008, they found an asteroid that hit the Earth 16 hours after they discovered it. It was only 4 metres across, but it was a fairly significant event because it's the first time they'd ever done that. That was called 2008 TC3. It was 6th of October in 2008. It hit in the Sudan. But the techniques had improved so much that the astronomers were able to predict within 200 kilometres of where it landed. So that was significant.
Is that 90% target when you don't know what 100% is?
That's probably a good question. And I don't think I think they probably had an idea of, they probably did some maths and thought, there's a fair bit of it out there, so, let's set the bar here. But I think some of the scientists were genuinely surprised that there was a bit more out there than what they thought. So the other one is Apophis, which was a close approach in 2004. And for a while, this was quite high on the Torino scale, which is the scale they use to rate the danger of an asteroid hitting the Earth. So Apophis is 350. It'll miss the Earth on April 13th, 2029 by about 5 or 6 Earth radii. So it's going to come very, very close. But because it's been studied so long, and we've had radar scans of it as it's gone past, and astronomers have put in some big time on this one to get it. So with an asteroid, the more you measure it, the narrower the zone of uncertainty is. So if you have an asteroid here with a zone of uncertainty here, and the Earth is going to kind of wander around near that zone of uncertainty, you can't kind of eliminate that it's not going to hit the Earth. So what they do is they try and get more and more accurate readings, so the zone of uncertainty comes down to a point where they can categorically say it's going to miss. Right? So, but there's a thing called the resonant return window, which is a little 650 metre wide window. If it goes through that keyhole, it'll come back 6 years later and hit the Earth. But they won't know until after it's gone past. So this is important. What we're doing today, this is important, right? So as I've always said, catastrophic climate change is a basket of risk, which includes asteroids and tectonic plate shifts as well as all the other stuff you've heard about.
What would happen if you did it today?
So, well, So the traditional theory depends on what type of asteroid it is. So if it's a carbonaceous asteroid, which is made up of, organic and softer material, it's going to be different to a stony metallic asteroid we mentioned before. So one of those, obviously, but the theory is that anything less than 80 metres will kind of mostly burn up in the atmosphere, although some rocks and rubble kind of maybe. The little 8 metre or 4 to 8 metre one, there were 15 kilograms of rocks that they collected in the desert after that came in. So it wasn't too bad. So if this came in, its trajectory comes in over Europe and down the east coast of the United States. So
That's okay.
So, you wouldn't want it landing in the Pacific Gulf of California, put it that way. But astronomers are certain it's not going to hit in 2029, but this was another big wake-up call that, this is really important that we actually get this stuff and we know what's out there. 2001-955 is called OSIRIS-REx. Sorry, it's not called OSIRIS, that's its name. But the mission to go to it and collect a sample and come back is called OSIRIS-REx. Now, I'm not sure if I've got it in there, but Origin, Spectral Interpretation, Resource Identification, Security, Regolith Explorer. There's a good acronym for you. So someone's dreamed this up over there at the University of Arizona, and so a regolith is like a crusty thing on the outside that kind of, so carbonaceous asteroid is one that's thought by scientists to have the origins of life and the amino acids and some of those kind of stuff in them. They're not just really hard, stony metallic rocks. So carbonaceous asteroids like that one, we can't actually have a look at that one tonight, but because it's very close to the sun now, but what the OSIRIS-REx program is getting astronomers to look at a group of 70 asteroids that are like it, like that one asteroid, so that they can get the characteristics of the carbonaceous asteroid, the spin rate. It's not all about the size, the spin, their orbits, how accurate that orbit is, and they're studying 70 of them like that over the next 16 years, because in 2016, the mission is going to take off to go and visit that asteroid 101955. Now the thing about 101955 is that it's going to come even closer than Apophis. It's got a 1 in 1800 chance of hitting the Earth in 2182, and it's 530 metres. That's big again as Apophis. So it's quite a dangerous. So this is the most dangerous of the potentially hazardous asteroids that scientists know about. So, in the true sense of what we've heard about citizen science, the OSIRIS-REx mission has been set up by the NASA Goddard Space Center and the University of Arizona to track that asteroid and 70 just like it out to 2016, so that when they go there, they know what to expect. They know the characteristics of this asteroid. Because what they're going to try and do is send a spaceship to it, grab 30 grams of it, and bring it back to Earth, and we sample that and find out a bit about the asteroid. So that 2182, if they do need to do something about it, then they'll know what to do. So, what would you do about an asteroid that was in danger of wandering too close to the Earth? Any ideas? Blow it up, Bruce Willis. Push it out of the way. Yeah. So, the general thinking is if you blow it up, you just break it up into small bits that could still hurt you. The two of the more evolved ideas spray paint it with something that reflects the sun a bit more than what is there now, or use a gravity tractor, so get a big satellite, pack it full of depleted uranium so it's nice and heavy, and just pack it alongside it, and it'll just gradually drag it off course. So there are two of the, but you need enough time to plan that and get it done. So how would we know how to do that? Well, that's what astronomers, amateur astronomers, professional astronomers do. So we're going to have a look tonight at how we do some of that. When we're looking at asteroids, and this is a fairly complex citizen science project, so we'll have some fun with it, and then we'll go back to some of the other things, the simpler ones tonight. So firstly, you go to the Minor Planet Center, you get the coordinates of where the asteroid is, you then log on to your telescope, you set up an observation run, download images, you compare what's in your image to the star maps, and you convert every pixel to what we call a plate scale. So depending on the star map, mathematically compared with your photo, it gives you arc seconds per pixel, and you can then plot the course of that asteroid and get the right ascension declination coordinates I was talking about before. And then you blink 3 images, which is what we're going to do, and then you can measure the asteroid position and report the data. Now, as I said, it's raining in New Mexico, so I can't log on to my beautiful telescope. But 3 nights ago, I took some images. It was fairly early in the night, it was a little bit grainy, but we're going to have a look at that right now. So let's have a look at that. So where do we go to get this? So the Minor Planet Center is the source of, next time someone tells you someone's hiding an asteroid from you, this is where you come. You just type the name of it in here, tell them your latitude and longitude on Earth, and it'll tell you where to look. So some of them are around the other side of the solar system, so you won't see them until they come back. Asteroids get lit up when they're opposite the sun and travelling by us. It's what they call opposition when it comes to a point. So they go all the way around the back of the solar system and can't really see them. When they come close to Earth and they're opposite the sun is when they're all nicely lit up and we can photograph them. So in here we have a minor planet ephemeris tool, which is this one here, and we can go, so the asteroid that we're looking at, I'll just show you 10302, which is a numbered asteroid. This is a carbonaceous asteroid, it's on the list. We type in my observatory code, which happens to be just an allocated code that they give me, where it's got the defined point of latitude, longitude, where my telescope is. If you don't have that, you can just type in your latitude and longitude here and your elevation above sea level. And then we click on hours, and then we hit get me the ephemeris of the asteroid, and it will show you here. Here it is, 1989 ml, 10302, and this is where it is, so we know this is the latest hour here. So if you can see, I had picked this one out because, as you can see, the object is 50 degrees above the horizon in New Mexico at the moment, so it would have been a good spot for viewing tonight. So we can just, what we do is we run an image series, we type in 10302, we put the right ascension in there, paste. So here we then pick how many images we want, so we want at least 3, but I usually allow more because you need more. And then we can pick the duration of the image, the filter that we want to use. So it's really, and then we plate solve our images. We can do a little thing called a dither, which just moves the telescope a little bit so that the pointing angle, if there's any artifacts in the photo, don't drift across the image like asteroids, so you don't confuse them. And then you acquire the images and away you go. So, as I said, that's what the sky looks like, so we won't be doing quite that tonight.
About focusing?
Yeah, so there's a little routine, a lot of software in this telescope. It's got focusers, it's got telescope controller, and what it does is it takes a photo and then moves it and compares the point spread function of the stars, and where it's got the tightest star, it knows it's in focus and it goes, yep, I'm in focus, and away it goes. And we have a fallback position where for certain filters we have a focus point, and it just counts out the step motor, a certain number of. So here's a program called Astrometrica, and this is what we do with the images. So so we're going to look at an asteroid I took the other night, and I'll just show you how we do this, because and then we'll get back onto the moon mapper. So library, documents. So we're going to have a look at, as I said, there's 70 of them. There are 2 that are mainly visible at the moment. Here's one I took the other night. So we can take these ones, we'll open these images, and this is, I'll show you what this is. So it's an inverted image so that it doesn't hurt my 51-year-old eyes. So that's what happens when the telescope's not guiding properly. So what happens, we have an equatorial mount on a telescope which has got a big counterweight down here, and it kind of follows the stars across the sky. When it gets to a certain point, it's got to stop and then flip around the other way and then go down to the horizon. It's what you call a meridian flip, and if you don't plan your observation run carefully, you have a meridian flip right in the middle of your run, which is what that is. So we won't be looking at that image, that one, or that one. So these are 9 300-second images, so we've deleted 3 out, so there'll be 1 position, 5 positions, and then it jumps a bit. So we'll actually be able to see boom, 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 like that. So let's try. So like, yeah. Sorry.
Is there a reason you use 300 seconds?
Yeah. So that's a really good question. So it depends on how bright the asteroid is, as to how much light I can gather with the camera. But secondly, how fast it's moving, right? Because if it's really faint but going really fast, it'll be streaked, and if it's streaked, I can't actually measure its position, which is not good. But you have to kind of get enough light.
Isn't the start and end point of the streak enough, given the...
Yeah, it is, but we're talking about 1 or 2 arc seconds per pixel here, and kind of the cutoff is about 3 or 4 in your accuracy, otherwise it's going So that's a really good question. So it's about how fast the asteroid's moving. Now what we can do, if the asteroid's travelling slow enough, we can take multiple images and stack them and add them together to build the signal to noise ratio, which is something we do as a, so we like take 15 images and then stack them in 3 groups of 5 and then blink the 3 final images. So always take more images because you're going to have problems like we just saw where a couple of them didn't turn out. But let's blink this. So what this does, what it's doing is just looking at the image. So an astronomy photo is just like an Excel spreadsheet. If you think of it, right? It's a CCD camera, which is a charge coupled device. So every pixel just measures the amount of light that hits the pixel, right? And then it it's either dark or it's bright, and depending on, so most of these have what they call a well count. It's like a bucket. So as soon as 65,000 photons of light hit that bucket, it's full. So, and you can see that one up there went over full because it's starting to creep out across, so it's a very bright star. What you can see there is actually satellites. So because this was fairly early in the evening, we're in that zone. Usually asteroid hunters like 3 o'clock in the morning because the air is really still. There's no satellites crisscrossing the images, but that will show you what it is. So there are a couple of asteroids in this image, and I'll show you how we can look at them in a minute. But I'm just going to zoom in here and pull it down to, and let's check. Where is he? Now you can see this one here that's streaking across there. Sometimes you get space debris that's tumbling. Now, can you see, near where that crosshair is, can you see something moving? Right? Just here. So he's going boom, 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 and then jumps a bit because we've cut out those 3 photos. So that's what we look for.
And so there you have it, folks. A world first, a NASA Goddard Space Center citizen science mission in a Melbourne cafe. We wrapped up the session with further citizen science activities from CosmoQuest. We looked at the moon mapper, mapped some lunar craters, and took a look at the Ice Investigators project. Other citizen science activities at Zooniverse, and of course you can always join your local astronomy club or use itelescope.net. Good evening.